Okay, so one application of this orthogonal projection is going to be what's called linear regression, and we're going to use the techniques of least squares. And I know it's something you already saw with Mr. Biles, so let's give it another go to show how it happens in the context that we have presented. Okay, so basically the idea is that you've got a series of observations. Okay, you've got some observation xi with a corresponding yi. Okay, so you've got a list of couples of pairs xi, yi for some I belongs to some set of integer 1 to n, let's say, and it's going to make a scatter points. Okay, and the idea of linear regression in general is to find one way, a line, a nice line, to fit those observations, right? You want to find the equation of a line, so that is represented in 2 dimensions. Y is equal to ax plus b, such that in some sense it's going to be the closest to your scatter points, right? You want to minimize, we want to minimize the distance between the line of equation y is equal to ax plus b. So basically, we're looking for unknowns a and b, okay, that are going to define the equation of the line, and the observations, okay, and the observations being the xi, yi, okay. So you want that if you plug in xi in this line equation, so you get axi minus b. It's close to, in some sense, to the yi. Okay, so you want to the yi that you have observed. Okay, so what is that used for? It's basically used for projections. Well, projections in the sense that if you are given some value, you want to be able to determine what should be. If you're given some x, you want to determine what should be the corresponding y. Okay, and so if you have observation of some, I don't know, physical quantity or economical quantity on some given period of time, you want to be able to determine what it's going to be next year, next week, tomorrow, whatever. That's one of the applications. Okay, so let's see how we can treat this problem. Okay, so we're going to say that our observations xi, they are making the vector x. Okay, x is x1, x2, xn. So that's a vector of Rn if all the xi's belong to Rn. Okay, and similarly, we're going to create the vector y's of the corresponding values, y1, y2, yn. So that belongs to Rn. Sorry, I forgot the n above. All right, and we are looking, well, we are making this line ax plus b, okay? We are making the z, right? The z, which are going to be a times, that's a vector of Rn, so that's going to be a times the vector x1, x2, xn, plus b, which should be written as b times the vector 1, 1, 1, 1, 1, 1. Okay, so that for each z is also a vector of Rn with coordinates ax1 plus b, ax2 plus b, etc., axn plus b. And basically, we want to make the difference between, we want to find A and B such that the difference between the vector Z that we have created out of our observation x with the coefficients, with the unknown coefficients that we want to find a and b, we want to minimize that difference between z and the yi's, okay, the observations, the real observations, the values we got from the experience, from the experiment, okay. So find a and b such that the difference between z and y is minimal. Okay, so now that we know how to define distances, that's good. We are going to minimize the norm between z and y. Okay, so we want to find a and b such that we want to minimize on all of the possible values of real values a and b, such that the norm of z minus y is as small as we want. Okay, all right. So the norm of, let's take the norm square. That's the same thing, and so we want to minimize. If you expand that norm, we want to minimize the sum of zi minus yi squared. So from 1 to n, we want to minimize on all ABs, the sum of so AXI plus B minus YI squared. And hence the name least squares. We want to find A and B that make those squares, the square here, as small as possible. So let's do some linear space, orthogonal projection, interpretation of this problem now. Okay, so let's observe our Z. It's going to be equal to some coefficient A times vector x plus some coefficient b times this vector 1, 1, 1. So in other words, in terms of linear space, we could say that Z belongs to the span of x and that vector 1, if I say that. This is my notation for this vector. Okay? All right. So Z belongs to the span of these two vectors. All right. So basically, what are we looking if we want to find Z minus Y in terms of norm that is smallest, as small as possible? We know that the minimum of this norm is going to be attained for Z is equal to the orthogonal projection on the space that is spanned by x1 of the vector y. Okay, that's absolutely the direct interpretation, knowing the definitions. All right, we're looking for the smallest norm, so we know it's called the distance between y and the space that is spanned by the vectors of the vector that contains only ones, all right, this one, and the vector that contains our observations xi. Okay, so what does it imply? Now we know that Z is the this orthogonal projection. It implies that y minus Z is orthogonal to x on one hand, and as Z is the orthogonal projection of y, and y minus Z is also orthogonal to 1. Okay, so that's giving you these two equations in terms of scalar product. That scalar product of x with y minus z is equal to 0, and scalar product of 1 with y minus z is equal to 0. Now, if I expand that a bit further, I'm just working on those two equations, on that system of equations. What do we get? So x y should be equal to xz. And now I rewrite that z is equal to ax plus b times 1. So that gives me that x y should be equal to ax plus b times 1. Expanding by linearity gives me a, so norm of x square, x scalar with x, plus b scalar product of x with 1. Okay, that's for my first equation. Second equation gives me 1 with y, 1 scalar with y is equal to, so 1 scalar with z. And so again, expanding by linearity, that gives me that that's equal to 1 ax plus b times 1, which is equal to a x with 1, okay, and plus b norm of that one vector square. Okay, good. That's it. That's it. We've got our two equations. Basically, we are looking for A and B. All right. So let me make that a bit more obvious. These are our unknowns. Okay, and we have A times norm of x squared, which of course you can calculate. Norm of x squared is the sum of xi squared. These are your observations. Scalar product of x plus 1 and x and 1. Well, we had one exercise where we worked on that. Scalar product of x and 1, that's just the sum of xi, are my observations. And what else do I have? Xy is just going to be the sum of xi, yi. 1y or 1y1 is just the sum of yi. Okay, so eventually what do I get? I get a, my unknown a times my sum of xi square, plus b times my sum of xi is equal to sum of xi yi. And first equation, second equation was a sum of xi plus b sum of ones. Okay, from 1 to n. All my sums go from 1 to n being my number of observations, 1n, and that's going to be equal to sum of yi, I 1 to n. Okay, and so basically you've got that's a matrix equation. Okay, sum of xi, yi, sum of yi, and your matrix here is, sorry, my matrix in front of it is just given by so xx x 1, sorry, 1 x 1 and 1 1. Okay, and that's it. You just have to invert that matrix and find AB by calculating, well, if you call this that's matrix, I don't know, whatever, calculate m minus 1 times, so you've got sum of x, so x y times y1. Okay, you apply, and that's going to give you your AB, your unknowns AB. And this is it. It's the least squares. And actually, you can extend that to things a bit more complicated, but maybe we'll do that another time. Okay, good.